All right, I'm back. So I went ahead and reapplied the calibration there. I'm going to show you a few more samples to just show you exactly what's going on. Now I've changed the scale here. This is the resonance that occurs approximately 1 gigahertz. Now you can see that the frequency is actually 973 megahertz. Depending on your actual device, it may vary just a little bit, but I've actually built two of these and they do come in right around 970, plus or minus a little bit. The actual frequency doesn't matter so much. What matters is the change. So if we start to look at a few materials, let's take a look at the PCB material first. This is FR4 or some sort of FR4 similar material. We're going to head and throw this in the measurement chamber. When we do that and we find our position there, you can see the frequency shift and also the noticeable Q shift. See how the marker has gone up quite a bit from approximately -1 to approximately wherever that marker is, 0.8. So that is the loss. And the frequency shift we can use to determine the dielectric constant, which for this material I think we're actually going to find out is around 4.6. All right, material number 2. This is a ceramic and aluminum oxide, I believe. We will go ahead and throw that in the chamber. This is a slightly larger sample, which we didn't have a lot of choice on this. And there you go. Look at the frequency shift. Notice how much it's shifting. And notice also that that marker is pretty dang close to the original marker because the loss of this material is rather tiny. So that's as expected. Everything looking good there. All right, next material, let's look at Teflon. Teflon has a dielectric constant of approximately 2.1. It is approximately lossless. So we should see a moderate frequency shift and essentially no loss. So I'm getting that in position, and there it's in position, and it's exactly what you see. Very little loss and a little frequency shift. Again, the frequency shift is also based on the physical size of the sample. So that will come into our calculation later. Don't take these things and think you can just calculate them all the same, because physically these samples are different, and that's an important part of the calculation. All right, so that was our Teflon sample. Next we have a piece of green foam. This is insulation foam, sold at your local home improvement store. If you're in the United States, they sell this stuff that you stick on walls to insulate. It turns out that both the green and particularly the pink foams that you can buy are pretty close to lossless and are very good for antenna testing and things like that, because they're low loss materials. You can buy the expensive stuff, but if you're watching my video, you probably don't care to do that. All right, so I'm going to go ahead and shove this in the chamber here very carefully, and there you see, tiny shift in frequency, tiny shift in terms of Q value and loss. And that is precisely as expected. Voila. In terms of other materials we have here, this is the expensive foam. This particular sample is not the Swiss stuff, this is the Chinese stuff. But still, this is the stuff that people use for like aerospace applications. It's supposed to be low loss rigid foam, and what you will see here is it is indeed that. I've got it in the chamber now, but you will also see that essentially has no difference versus the previous sample. This one is showing a little bit higher loss and a little bit more of a frequency shift, but that's also because it's a slightly larger sample. That difference will come out in the calculations done later. All right. And then we have a random piece of some sort of plastic. We sometimes don't know what our samples are, but we still have to figure out the dielectric constant. So let's go ahead and throw that in. And we'll put that into the measurement system. And what do we see? Well, we see a pretty significant shift and a ton of loss. So this is a rather lossy material. Again, a slightly thicker sample, but still, this amount of loss indicates that it's the lossiest material that we've tested so far. Now, if we want to keep our life interesting, because why not? RF engineers are interesting people. Ha 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 ha. Let's go ahead and measure some other things. We have here a piece of walnut, black walnut. So let's go ahead and see what happens when you throw black walnut in here. There it is in the measurement position. And we see clearly a shift in frequency, but also a ton of loss. This is the lossiest material we've tested thus far, and we are not surprised because wood is lossy. So again, this method is robust and it can be used for all sorts of materials, including wood. Now, if you are using wood, note that wood is not uniform, and it will have properties which depend on the moisture in the air, the moisture content of the wood. So expect your measurements to change over time. Here is a piece of oak, just for fun. So let's throw the oak in and see what we get. So measurement position is roughly steady there, and yeah, not completely dissimilar to walnut. Again, high loss and a moderate frequency shift. So we'll go ahead and pop that out of the chamber. Now, in real life, I would have saved each one of these measurements and used those for the calculations. But in this case, I have already saved that data and I've already done the calculations. So due to the magic of television, we can just jump right there. Let's do it.